Right now, as you watch this video, billions of invisible particles are streaming through your body every second. They pass through your skin, your bones, the chair you're sitting on, and the entire planet beneath you, without leaving a trace. Astronomers have spent nearly 100 years trying to figure out what these particles are. They've built detectors a mile underground. They've launched space telescopes. They've mapped galaxies across billions of light years, and they still don't know. Welcome to the strange, frustrating, absolutely beautiful mystery of dark matter. Here's something that should genuinely shock you. Everything you've ever seen, everything every telescope has ever observed, every star, every galaxy, every cloud of gas drifting between the stars, every planet and moon and asteroid and human being, all of it added together, makes up only about 5% of the universe. 5%, that's it. Roughly 27% of the universe is something called dark matter. The remaining 68% is something even weirder called dark energy, but that's a story for another video. Today, we're focused on that 27%. Because here's the thing, dark matter outweighs ordinary matter by more than 5 to 1. There is over 5 times more of this mysterious stuff than there is of the atoms that make up stars, planets, and people, and we have no idea what it actually is. Now, when scientists say dark matter is dark, they don't mean it's black like coal or shadowy like a moonless night. They mean it's truly invisible. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. Beams of starlight pass straight through it as if it weren't there at all. So how do we know it exists? How can you possibly study something you can't see? The answer is one of the most elegant detective stories in science. Our story starts in the 1930s with a Swiss-born astronomer named Fritz Zwicky. Zwicky was studying a group of galaxies called the Coma Cluster, and he was trying to figure out how much it weighed. He did this by measuring how fast the galaxies were moving around inside the cluster. Imagine a flock of birds wheeling through the sky. If they're flying really fast, gravity has to be strong to keep them flocked together. They just scatter into the distance. When Zwicky did the math, he got a result that didn't make sense. The galaxies were zipping around so fast that the visible matter, all those stars he could see, couldn't possibly hold them together. The cluster should have been flying apart like a piñata exploding in slow motion. But it wasn't. It was perfectly intact. Something else, something invisible, had to be providing the extra gravity. Zwicky called this mystery substance Dunkelmaterei. That's German for dark matter. For decades, his idea was treated as a curiosity, a weird footnote, until a remarkable astronomer named Vera Rubin came along. In the late 1960s and through the 1970s, Vera Rubin and her colleague Kent Ford were measuring how stars move inside spiral galaxies. They started with our galactic neighbor, Andromeda, then moved on to dozens of others. What they expected to find was simple physics. Think of our solar system. Mercury, the closest planet to the Sun, whips around its orbit at about 47 kilometers per second. Neptune, way out at the edge, drifts along at only about 5 kilometers per second. The farther you are from the center, the slower you move. That's how gravity works when most of the mass is concentrated in the middle. Galaxies should behave the same way. Stars near the bright, dense center should orbit fast, and stars at the edges, where the visible matter thins out, should orbit slowly. But that's not what Rubin and Ford saw. The stars at the outer edges of these galaxies were moving just as fast as the stars near the center. Galaxy after galaxy, the same impossible result. It was as if Neptune were orbiting the Sun at the same speed as Mercury. Something was very, very wrong, or rather, something was very, very right, and our picture of these galaxies was incomplete. Rubin realized that for the math to work, Each galaxy had to be sitting inside a giant invisible halo of matter, extending far beyond the stars we can see. This unseen mass was contributing extra gravity, pulling on those outer stars and speeding them up. By her calculations, galaxies must contain roughly 10 times as much dark mass as visible mass. Rubin once said, "What you see in a spiral galaxy is not what you get." It's a beautiful summary of her life's work. The universe, it turned out, is mostly hidden. For a long time, skeptics could push back. Maybe Rubin's results meant gravity itself works differently on huge scales. Maybe we don't need invisible matter at all. Maybe we just need to tweak Einstein's equations. This idea, called modified Newtonian dynamics, or MOND, has had its supporters and still does today, especially because it explains galaxy rotation surprisingly well without invoking anything invisible. It remains a real scientific debate worth taking seriously. But then, in 2006, astronomers studied something called the bullet cluster, and the evidence for dark matter became almost impossible to argue with. The bullet cluster is what happens when two enormous clusters of galaxies collide. Picture it: thousands of galaxies in each cluster, plus huge clouds of hot gas filling the space between them, smashing into each other at millions of miles per hour. The collision sorted the contents of these clusters by type, like a cosmic centrifuge. The hot gas, which makes up most of the ordinary matter, slowed down due to friction and bunched up in the middle of the wreckage. The galaxies themselves, which are mostly empty space, sailed right through and continued on. And the dark matter? Astronomers used a trick called gravitational lensing, where massive objects bend light from galaxies behind them, to map where the mass actually was. They found something striking. Most of the mass in the bullet cluster wasn't with the gas. It had passed straight through, traveling along with the galaxies, like a ghost moving through walls. The visible matter and the gravitational mass were in different places. There's no easy way to explain that with just modified gravity. There has to be something there, something invisible, that doesn't interact with gas or light, that just keeps moving when stuff collides. Dark matter passed the test in dramatic fashion. Once you accept that dark matter exists, something extraordinary clicks into place. Dark matter, it turns out, is the scaffolding of the entire universe. In the moments after the Big Bang, tiny ripples in density spread through the early cosmos. Dark matter, untroubled by light or radiation, was the first to clump together under gravity. It pulled itself into vast halos and stretched into long filaments, weaving an invisible cobweb across hundreds of millions of light years. Ordinary matter, the gas that would eventually become stars and planets, fell into the gravitational wells these dark matter structures had already carved out. Galaxies formed inside the densest knots. Clusters of galaxies formed where the filaments crossed. Without dark matter, there simply wouldn't have been enough time or enough gravity for any of this to happen. We now have stunning maps of this structure. In January of 2026, scientists using the James Webb Space Telescope released one of the most detailed dark matter maps ever made, showing the invisible scaffolding wrapped around galaxy clusters in extraordinary new clarity. Wherever there's a big cluster of galaxies, there's an enormous concentration of dark matter. Wherever galaxies string together in long bridges, dark matter strings along with them. The visible universe traces the invisible one, like frost outlining the branches of a tree you can't quite see. Here's the part that keeps physicists up at night. We know dark matter exists. We can measure its gravity. We can map where it is. We just don't know what it's made of. The leading candidates are tiny subatomic particles that haven't been discovered yet. The most famous is called a WIMP, which stands for Weakly Interacting Massive Particle. WIMPs are predicted to be heavy, sluggish, and almost completely invisible to ordinary matter. Another candidate is the axion, a particle that would be incredibly light, perhaps a trillionth the mass of an electron. There are also more exotic ideas, like primordial black holes from the early universe, or whole families of dark particles forming a kind of shadow universe alongside our own. To test these ideas, scientists have built some of the most sensitive instruments ever made. Deep beneath the Black Hills of South Dakota, nearly a mile underground, an experiment called Lux Zeppelin sits in a vault filled with 10 tons of ultra-pure liquid xenon. The whole thing is buried so deeply to shield it from cosmic rays. The hope is that, once in a great while, a dark matter particle from our galaxy's halo will collide with a xenon atom and produce a tiny flash of light. As of late 2025, after over 400 days of looking, Lux Zeppelin has set the strongest limits ever on these particles. But it has not seen one. Not yet. Meanwhile, the Vera C. Rubin Observatory, named after the astronomer who put dark matter on the map, took its first images in June 2025. Over the next decade, it'll survey the entire southern sky again and again, mapping the cosmic web in unprecedented detail and giving us our best chance yet to figure out what dark matter is doing. So why should you care about a substance you'll never see, touch, or feel? Because dark matter built the world you live in. Without it, there would be no Milky Way, no sun, no Earth, no you. Galaxies wouldn't have formed in the time the universe has existed. The cosmos would be a thin, formless soup of gas drifting through empty space. Every time you look up at the stars, you're seeing only the lit-up tip of a much larger, much darker iceberg. The bright stuff we love and study is just the foam on top of a deep, invisible ocean. And we are, somehow, the kind of creatures who can figure that out. We can detect the undetectable through its gravitational fingerprints. We can map its presence across billions of light years. We can build machines a mile underground to listen for the faintest whisper of its particles. We just can't yet name it. Maybe in the next 10 years, with new telescopes coming online and new detectors getting more sensitive, we'll finally crack it. Or maybe dark matter will keep its secret a little longer, sitting there, quietly holding everything together while we keep looking. If you enjoyed this trip into the unseen universe, hit that subscribe button and let me know in the comments what cosmic mystery you'd like to explore next. Maybe dark energy, maybe black holes, maybe what was happening before the Big Bang. Until then, keep looking up. The universe is stranger and more beautiful than we'll ever fully understand, and that's exactly what makes it worth studying.